We have been discussing the Klein Gordon equation, the simplest relativistic quantum mechanical equation, over the last couple of lectures. Let me quickly recapitulate some parts of what we had done there. The Klein Gordon equation itself can be written in this compact form: box plus m square c square by h cross square acting on phi equals 0, where box, the four-dimensional generalization of the Laplacian, also called the D'Alembertian operator, can be written in relativistic notation as del lower mu del upper mu, or del 0 whole square minus Laplacian. Now, if we look for a wave-like solution to this equation, given by phi equals e to the minus I over h cross p mu x mu, where p mu's are just constants, substituting this into the Klein Gordon equation immediately gives rise to the result that p lower mu p upper mu, the norm squared of the P4 vector, must equal m square c square. And that is exactly the relativistic energy momentum relationship: P0 whole square minus P vector square equals m square c square, which, with the identification that P0 is E by C, gives us the familiar relativistic result: E square equals P square c square plus m square c to the 4. As we pointed out there, this implies that the energy E can have two values, both positive and negative, and that was one of the major shortcomings which the Klein Gordon equation had. That, coupled with the fact that it gives rise to a conserved probability density like quantity, which cannot qualify as a probability density simply because it is not necessarily positive definite. Now, putting aside these problems for the time being, let me just remind you that we can write down the two solutions, the positive energy and negative energy solutions, using this quantity P0, which is a positive square root of P square plus m square c square, in these two forms. So we have phi P1 of x, which is e to the minus I by h cross, times P0 times Ct minus P vector dot x, that of course is P mu x mu, and phi P2x is e to the plus I by h cross P mu x mu. So we can put them both together and write phi Px R, that is where R is an identifier which tells you which of one of the two solutions you have, is given by the quantity e to the minus I by h cross times the number epsilon R times P mu x mu. Epsilon R is plus 1 for our first solution, that is R equal to 1, and minus 1 for R equals 2. So both the positive and negative energy solutions can be written down in this compact form. There is just one important point to make about these solutions. Phi P1x is an energy eigenfunction with energy eigenvalue plus P0c, that is square root of P square c square plus m square c to the 4, the positive square root that is, and is also a momentum eigenfunction with momentum eigenvalue equal to P vector. Phi P2x, on the other hand, is both an energy eigenfunction and momentum eigenfunction with the energy eigenvalue as expected is minus P0c, and hence is minus square root of P square c square plus m square c to the 4, the infamous or famous negative energy solution. What might come as a bit of a surprise is that the momentum eigenvalue for this particular version is actually minus P. We have deliberately used this notation for phi P2, where phi P2 is an energy eigenfunction with negative energy, and also it is a momentum eigenvalue which is negative of the label that is used to actually write down the function. The reason behind that will be clear after we talk about the particle-antiparticle interpretation of these energy eigenfunctions, but that will be in some later lecture. In today's lecture, we will focus on this question: how far can we go in creating a single particle quantum mechanical theory consistent with the Klein Gordon equation, despite the problems that we outlined a while ago. So, the occurrence of negative energy solutions is a real problem, but it is not a problem for free particles. If you recall why, there is an energy gap between minus mc square and plus mc square. So if you start with a positive energy beyond plus mc square, because energy is conserved for a free particle, there is no chance of that being found in negative energy eigenstates. So the negative energy eigenstates which are present as solutions to the Klein Gordon equation will not bother us as long as we are dealing with a free particle. So a particle which is in a positive energy state will forever stay in a positive energy state. And in fact, if you go through the calculation of the probability density rho, or what we wanted to call the probability density rho, it will turn out that for a positive energy state like this, rho actually is positive and will remain positive for all times. So this seems to indicate that a consistent theory can be developed for a free particle by restricting our solutions to only positive energy states. So although the Klein Gordon equation actually has positive energy and negative energy solutions, we would just consider the positive energy solutions and forget about the negative energy solutions. If we wanted to do this at the level of the equation itself, the effective equation would end up being this: IH cross del phi del t equals square root of m square c to the 4 minus h cross square c square Laplacian acting on phi. Now this first order equation with its Laplacian under the square root sign may look very formidable, and in fact it is very formidable if you want to talk about all possible solutions. But as long as you keep yourselves restricted to positive energy solutions only, this can be handled rather neatly by adopting the Fourier transform. What we are going to do next is we are going to apply a kind of partial Fourier transform to phi of x. I say partial because we are actually Fourier transforming the spatial variables x1, x2, x3 and replacing them by k1, k2, k3, the three components of k vector, while keeping x0, the temporal variable, intact. So once you do that, once you take this particular Fourier transform and plug it into the differential equation, it gives rise to a corresponding differential equation for chi. And that's a pretty straightforward differential equation. And you can easily see that the Laplacian acting on the e to the ik dot x. Note that the Laplacian, consisting entirely of spatial derivatives, act only on the e to the ik dot x term in the Fourier transform, and that replaces basically the Laplacian by minus k vector squared. And once you take that into account, the first order differential equation you obtain for chi is simply IH cross del 0 chi, or 1 by c del chi del t, is h cross omega k by c chi of k x0, where omega k, the frequency corresponding to k vector, turns out to be essentially the energy by h cross. Now, this equation is very, very easy to solve, and it tells us that chi at k vector and x0 is simply e to the minus I omega k vector x0 by c times some initial value for chi, that is chi 0 k. Of course, this is our familiar e to the minus I omega t kind of behavior for a positive energy solution with energy h cross omega, simply because x0 by c is nothing other than our temporal variable t. So this makes it clear that I can write phi of x as a superposition of a bunch of positive energy solutions, and this superposition of course is none other than the Fourier transform that we have been talking about. Now this particular Fourier transform has a slight problem in the sense that it treats spatial and temporal coordinates separately, and hence realizing that its results are relativistically covariant may take a bit of thought. We will next try to express phi of x as a Fourier transform in a slightly different way, which will make the relativistic covariance of this phi of x, the fact that phi of x really is a scalar field, obvious. For this, what we do is Fourier transform all the four variables x0, x1, x2, x3 and bring in new variables k0, k1, k2, k3 in the Fourier space. So we are doing a four-dimensional Fourier transform here over d4k. In the standard manner, you have an e to the minus ikx function Then you have the corresponding Fourier transform. Now the Fourier transform has some special features here. Apart from some function capital phi of k, in fact some arbitrary function capital phi of k, which stands essentially for the amplitude of the Fourier component, we have two more factors. The delta function factor, delta of k square minus m square, essentially ensures that this phi of x satisfies the Klein Gordon equation. On top of that, we have another function as a factor, theta of k0. This theta is the Herbicide step function, which is 1 for positive argument and 0 for negative arguments. And what this does is ensures that only the positive energy solution, the one corresponding to positive value of k0, is there in your final result. In addition to all this, you have an overall external factor of square root of 2 by 2 pi to the 3 by 2. This is primarily for later convenience. But you have to realize that what we have done is we have traded the three-dimensional Fourier transform that we had done earlier for a four-dimensional Fourier transform. By the way, I forgot to tell you one thing. In order to simplify the expressions involved when we write down the four-dimensional version, what I have done is I have chosen special units in which h cross and c are equal to 1. So, in those units, of course, the omega k expression will simply be square root of k square plus m square. And chi k x0 would simply be to the minus I omega k x0 times chi 0 k and so on. This is being done just to simplify the expressions a bit. You can, of course, supply the necessary factors by using dimensional analysis if you want the equations to be back in standard units. One advantage of writing down this four-dimensional Fourier transform is that it is rather simple to describe the effect of Lorenz transformations on the function phi of k. For this, what we need to realize is that under a Lorenz transformation, the scalar field phi of x changes to a new function phi prime of x, which is given by phi of lambda inverse x. Basically, all we are saying is when you do a Lorenz transformation, x changes to x prime, which is lambda x, and the scalar field at the point x prime, the new scalar field at the point x prime must be the same as the old scalar field at the point x. And that leads us to the conclusion that phi prime, this new function, at x has to be phi of lambda inverse x, as we have stated. Now, this means that phi prime of x has exactly the same form as phi of x, except that x has to be replaced, of course, by lambda inverse x. So, this is what the form really looks like. Now notice that k dot lambda inverse x is of course not the same as k dot x. However, lambda inverse k dot lambda inverse x is definitely the same as k dot x. That's simply the invariance of a dot product under Lorenz transformations. But because this k is a dummy variable of integration, we can of course replace k by any other dummy variable I want. In particular, we can carry out the substitution k equals lambda inverse k prime. Now, under this substitution, what happens to the d4k measure? The answer is simple. d4k, the four-dimensional volume element, is invariant under d4k prime because for all proper orthochronous Lorenz transformations, the determinant of L is 1. Determinant of the Lorenz transformation matrix is either plus 1 or minus 1, but for a proper Lorenz transformation is always plus 1. Now, what about theta k0? Theta k0 is actually exactly equal to theta k0 prime. Although k0 changes to k0 prime under the Lorenz transformation, the sign of k0 does not change as long as we are talking about orthochronous Lorenz transformations. So, when you talk of a transformation which connects one inertial frame to another, it's always a proper orthochronous Lorenz transformation. Under that, theta k0 must be the same as theta k0 prime. And as for the argument of the delta function, k square minus m square, that of course is exactly the same as k prime square minus m square, the norm squared of a 4 vector being an invariant under a Lorenz transformation. Now putting all this together, we see that the transformed function phi prime of x or phi of lambda inverse x can be written down in this form, where instead of the k dot lambda inverse x, we now have lambda inverse k prime dot lambda inverse x, which is of course the same as k prime dot x. And we have replaced the k everywhere else by k prime. But finally, what we now realize is that k prime is a dummy variable of integration, so we can change the label to anything, including back to k. So phi of lambda inverse x, the new phi prime of x, the new scalar field, is given by root 2 by 2 pi to the 3 by 2 integral over d4k e to the minus I k dot x delta of k square minus m square theta of k0 phi of lambda inverse k. So this shows that when you do a Lorenz transformation, the original solution to the Klein Gordon equation, phi of x, changes to a new function phi prime of x given by phi of lambda inverse x, and that essentially is the same function as phi of x, except that in the Fourier transform, capital phi of k has been replaced by capital phi of lambda inverse k. So describing the Lorenz transformation's effect on Fourier space is rather simple. The Fourier transform function capital phi of k has to be replaced by a new function whose value is capital phi of lambda inverse k. And that's it. In order to clarify the connection between this 4-dimensional Fourier transform and our earlier 3-dimensional version, which you see at the top of your screen right now, what we are going to do is we are going to first perform the integral over k0. And in order to do that, we are going to exploit a property of the delta function. Now this delta function, delta of k square minus m square, can easily be written down in terms of k0 square minus k vector square minus m square being the argument of the delta function. And just by replacing omega of k by k vector square plus m square, what we can do is rewrite this as delta of k0 square minus omega square k. And now this simply factorizes into two terms, delta of k0 minus omega k into delta of k0 plus omega k. And we then make use of our very standard property of the delta functions to rewrite this in this particular fashion. The factorized form above clearly shows that this delta function has support only when k0 is either omega k or minus omega k. And as a result, you get two different delta functions, delta of k0 minus omega k plus delta of k0 plus omega k, weighted in each case by 1 by twice omega k. Now this is something which is pretty straightforward and something which you have done in your mathematical base courses before. Now we can use this delta function to trivially integrate over k0. Just remember that you also have a theta k0 factor, which is why the delta of k0 plus omega k term will not contribute at all, because the integrand ultimately has a non-zero value only for positive values of k0. Putting this all together, we see that the k0 integral can be trivially carried out, leaving behind an integral over the spatial components of k, a 3-dimensional integral, exactly the same kind of 3-dimensional integral that we had done earlier for our mixed Fourier transform. And here, in the e to the minus I k dot x, the k dot x actually can be split into two pieces, k0 t minus k dot x, k vector dot x vector that is. But what is important is k0 is no longer an independent parameter. Because of the presence of the delta function earlier, the integration has forced us to replace k0 by omega k. So exponent e to the minus I kx actually is e to the minus I omega kt into e to the I k dot x. And the capital phi function, which actually was a function of all 4 components of k, that is k0 and k vector, has now effectively become a function only of k vector, with k0 being replaced by omega k. So as you can clearly see that this is a three-dimensional Fourier transform with the Fourier factor e to the I k dot x, and the actual thing that you are Fourier transforming has a factor e to the minus I omega kt as our function chi of k and t had. In addition to that, this capital phi at omega k comma k vector is essentially the chi0 k vector quantity that we talked about earlier. I say essentially because there's an additional factor of 2 pi to the 3 by 2 root 2 and omega k in the denominator, and those two combined with capital phi at omega k comma k vector will give us chi0 of k vector. So this goes to show that our 4-dimensional Fourier transform is actually equivalent to the 3-dimensional one that we had written before. The advantage of the 4-dimensional version, of course, is that it is manifestly covariant relativistically. So if you use that, many relativistic calculations can be done much more simply than if you use something which is not manifestly relativistically covariant. So far we have seen that we can construct wave functions which have only positive energy terms in it, and as a result apparently avoids the problems with negative energies which the Klein Gordon equation has. But if we are going to do quantum mechanics with such wave functions, we have to make sure that we have a proper Hilbert space to begin with. Now, the important point is that the set of all positive energy wave functions, which you can construct by just taking the 3-dimensional Fourier transforms that we wrote down earlier, they actually form a complex vector space. Now this is something which is very trivial to show from the definition of a complex vector space, so I am not going to label this point any further. You should of course try to prove it yourself. However, in order to do quantum mechanics, as I have said, you need a Hilbert space, which is a complete inner product space. So first we need to define an inner product on our vector space so that we can at least convert it into an inner product space. Now it turns out that we can define an inner product on this space, and that inner product happens to be something which is motivated rather strongly by the density-like term which the Klein Gordon equation gives us. It is defined as follows. The inner product of two wave functions phi and psi is given by I times the integral over all space of the quantity phi bar del 0 psi minus del 0 phi bar psi. Please note that since we are using c equal to 1, del 0 and del t are the same thing. And you of course must have noticed that there are suffixes t which I have put in the notation for the inner product itself, as well as a suffix to the integral sign. What this implies is that we are going to take the two wave functions at the same time t, and we are going to not vary t while doing the integral, in the sense that this integral is being evaluated over a surface with constant t. We can write this down a bit more compactly by using the double arrow notation. It's simply the integral of I d cube x phi bar del 0 double arrow psi. The double arrow simply means this, that phi del psi would simply mean phi times del psi minus del phi times psi. So here we are talking of the same thing, except that we are talking of the double arrow derivative with respect to the 0th component, only the time component. Of course, you can recognize that if I put in phi equal to psi, that is, you take the norm squared of the wave function according to this inner product, you end up with the quantity that we had defined as equivalent to the probability earlier. In that sense, this is pretty similar to what we do in non-relativistic quantum mechanics. Of course, there would be questions in your mind as to whether this is a genuine inner product or not. Remember, in order to qualify as an inner product, a bilinear map from V cross V to C, that is, something which carries two vectors into a complex number, must satisfy certain properties. So let us take a look at whether those properties are actually satisfied here. As it turns out, they are. Two of the properties, the fact that if you were to interchange the two wave functions, that is replace phi comma psi by psi comma phi, the result becomes a complex conjugate, and the fact that this is linear in the second factor, are trivial to establish from the definition. What might give you pause is this demand that phi comma phi of t must be greater than or equal to 0, with phi comma phi t equals 0 if and only if phi is 0. Now why should this give you a pause? Because as I have just said, this phi comma phi essentially is nothing but the integral of the probability density kind of thing that we had talked about earlier, and one of the reasons why we had rejected that as a possible probability density is that it is not necessarily positive definite. Hence its integral, which is our inner product, does not seem necessarily bound to be non-negative, and definitely does not seem to imply that a zero value can only be achieved when the wave function vanishes. But remember, we are not doing this for all possible solutions of the Klein Gordon equation. Our Hilbert space, or soon to become Hilbert space, is nothing but a collection of solutions of the Klein Gordon equation which correspond to positive energy components. Now that is a very important restriction, and as I am going to show, once you impose that restriction, this particular definition does give you a genuine inner product. In order to see that phi comma phi is actually non-negative, let us rewrite the inner product in terms of the Fourier transform versions. That is, I write phi of x and psi of x, the two wave functions, in terms of the Fourier components phi of k and psi of k. I have actually used the 4-dimensional invariant version of this Fourier transform and then have carried out the k0 integral, making use of the delta function as explained earlier. So in this particular set of expressions, k0 is always given by omega of k vector. Now in order to calculate the inner product, at least what we are going to hope is going to be the inner product, we need the quantities phi bar, del 0 psi. It's easy to see that del 0 psi will give you an extra factor of minus ik0 from the x0 derivative, and phi bar psi is simply going to give you the plus ik prime x phi bar k prime integrated over d cube k prime. Putting them together, phi bar del 0 psi is going to be the integral that is indicated. And in this particular integral, I have tried to color code the contributions which have come primarily from the two factors. I didn't bother to do that for the 2 pi cube and the 2, which originates equally from both the factors. So this can be easily rewritten in the form minus I by 2 into 2 pi whole cube d cube k prime by k0 prime. So the k0 essentially cancels the k0s in the denominator, and then you have it e to the I k prime minus k dot x phi bar k prime psi k. The other term that we need to work out is del 0 phi bar comma psi, which turns out to be almost identical except that you have plus I instead of a minus I, and instead of a k0 prime in the denominator, you end up with a k0 in the denominator. As a result, when you combine the two together to form phi bar del 0 psi minus del 0 phi bar psi, which is the integrand that goes into our inner product definition, we get a 1 over k0 prime plus 1 over k0 from the two integrals. And then our inner product simply becomes an integral of this quantity over all of x. And all we have to do now is interchange the x, k and k prime integrals. In the original version, we were doing the k prime integrals first to get us phi bar del 0 psi and del 0 phi bar psi, and then we were integrating over x. What we are doing here is interchanging the order so that we get to do the d cube x integral first. And the d cube x integral is just an integral of e to the power minus I k vector minus k dot x. And a very standard result that you are all aware of is that this integral turns out to be twice pi whole cube times the three-dimensional delta function of k prime minus k. This should also explain why we started with a 2 pi to the 3 by 2 in the denominator for phi and psi. That is going to help us cancel out this 2 pi cube factor. The rest becomes very easy because you are now left with two integrals, one over k and the other over k prime. And using the delta function, the three-dimensional delta function k prime minus k, the k prime integral becomes trivial to do. So once you carry that out, the factor 2, which you get from 1 by k0 plus 1 by k0 prime becoming 2 by k0, also cancels the extra half. That also explains why you had a 1 by root 2 in the original definition. So finally, this inner product can be simply rewritten as integral of d cube k over omega k of phi bar k psi k. So, in terms of the Fourier components, the inner product, at least the thing that we are claiming should be the inner product, is equal to the integral of d cube k by omega k times phi bar k psi k. Note that phi bar k and psi k are actually functions of the 4 vector small k, but with the k0 component replaced by omega k. The one thing is obvious from this result, that if you take psi to be the same as phi, you are actually integrating phi k mod squared times d cube k by omega k, and that is obviously greater than or equal to 0, and moreover is 0 only when phi of k vanishes everywhere, and hence small phi vanishes everywhere. So our final important property that an inner product can have is satisfied. So as far as this particular product rule is concerned, it is a genuine, valid inner product. This formula also makes it obvious that this particular inner product is actually independent of the particular value of t chosen. Remember that there is a t in the notation, but that notation really indicates that when you are integrating, you are doing it at a constant fixed value of t. But on the right hand side, there is no mention of the t variable anywhere. So, this thing does not depend on t. Now this is a very familiar property also from non-relativistic quantum mechanics. After all, in non-relativistic quantum mechanics, wave functions evolve via a unitary time translation operator, and since both phi and psi evolve by the same unitary operator, the overall inner product does not change. Now, the one major difference which this particular expression for the inner product has compared to the non-relativistic formula that we have learned a long time ago is the presence of the 1 by omega k, which is coupled with the integration measure d cube k. The corresponding non-relativistic result would have simply been integral of d cube k times phi bar k psi k. So why exactly is there an extra 1 by omega k factor in here? Now, when we are talking about non-relativistic quantum mechanics, the major kind of symmetry operation that we talk about is rotations. And we want our inner product formula to be invariant under rotations. When you rotate your coordinate system, the k vector components also transform like the position vector does. In fact, all vectors transform the same way as the position vector. And this means that kx, ky, kz change. However, d cube k, the volume element, does not change under such a transformation. Why? Because when kx, ky, kz goes over to kx prime, ky prime, kz prime, the corresponding volume element changes by a factor which is given by the Jacobian of the transformation, or in this case, since the transformation is linear, simply the determinant of the transformation matrix. But as we had learned previously, the determinant for a rotation matrix is plus 1, and hence the volume element d cube k is invariant under rotations. However, Now we are talking about relativistic quantum mechanics, and the kind of transformation we are most interested in are Lorenz transformations, which of course include rotations, but there are also Lorenz boosts. Now, under a Lorenz boost, we have the phenomenon of length contraction, which means a three-dimensional volume element will not stay invariant under a Lorenz boost. So d cube k alone would not have been invariant. It turns out that d cube k by omega k, this particular ratio, remains invariant under the Lorenz transformation, basically because the way in which omega k, which is now the zeroth component of the 4-vector k mu, also transforms under a Lorenz transformation in exactly the same way that d cube k does, and hence the ratios does not change at all. Let us now give a proof of this very important result. Note that while you may not be using the Klein Gordon equation all the time in your later courses, anybody who does anything to do with relativistic quantum mechanics or even other things involving relativity would actually need this one result, that d cube k over omega k, or in terms of the energy momentum components, d cube p over e is an invariant under Lorenz transformations. This is actually a very, very useful result, going beyond just its applications to this particular inner product for Klein Gordon positive energy wave functions. Now, so let us just try to justify why this result is actually correct. The one reason is clear. In fact, we have already seen this. The way in which we arrived at this d cube k by omega k quantity is by integrating over k0 the invariant measure d4k times delta k square minus m square theta k0. Note that d4k is invariant simply because every proper orthochronous Lorenz transformation has a determinant of 1. Delta k square minus m square is invariant simply because k square is an invariant, and theta k0 does not change under an orthochronous Lorenz transformation. So because you started with something which is manifestly Lorenz covariant, which is manifestly invariant under Lorenz transformations, it stands to reason that what you get after you integrate over k0 is also invariant under Lorenz transformations. While this is a perfectly good argument, it may be more satisfactory to have a direct demonstration of this fact. Now, a general Lorenz transformation can be thought of as a combination of rotations and Lorenz transformations. Under rotations, d cube k, the volume element, of course doesn't change. Neither does the frequency omega k, because it's a scalar under rotations. So let us consider what happens under a general Lorenz transformation, which is not a rotation. That is a Lorenz boost. And for simplicity's sake, we are taking the boost along the one direction, that is along the x-axis. So we are considering this particular Lorenz transformation written in green. x0, x1, x2, x3 changes to x0 prime, x1 prime, x2 prime, x3 prime. And since the boost is along the one direction, x2 prime is the same as x2, x3 prime is the same as x3, but x0 prime and x1 prime are different from x0 and x1 in a very familiar manner. x0 prime is gamma into x0 minus beta x1, x1 prime is gamma into minus beta x0 plus x1, which is the very familiar standard Lorenz boost. Of course, under this, the components omega kx, ky, kz of the 4-vector k mu transform exactly like x0, x1, x2 and x3. So omega prime is exactly gamma times omega minus beta kx. That is, all you have to do is replace x0 by omega and x1, x2, x3 by kx, ky, kz in order to get these transformation relations. Kx prime is gamma times minus beta omega plus kx, ky prime is the same as ky, kz prime is the same as kz. Now, in order to know how the volume element d cube k changes under this Lorenz transformation, all you have to do is find out the Jacobian of the transformation. So, notice that in the Jacobian, what you have to calculate are terms like del kx prime, del kx, del kx prime, del ky, and so on. Now, since ky prime and ky are equal, kz prime and kz are equal, the second and the third rows of the Jacobian matrix, whose determinant you need to calculate, are trivially equal to 0, 1, 0 and 0, 0, 1 respectively. It is slightly more non-trivial to get the very first row. What you have to remember is omega is not independent of kx, ky, kz. Omega is connected to k vector by omega square equal to k vector square plus m square, and hence what we can always write is omega square d omega, omega square equals k vector square plus m square, and so omega d omega is simply k dk, kx dkx plus ky dky plus kz dkz. And so you can easily read off the partial derivatives del omega del kx, del omega del ky, and del omega del kz as simply kx by omega, ky by omega, and kz by omega respectively. So when you are actually calculating the partial derivative del kx prime del kx, you do have an overall factor of gamma, and the derivative of kx does give you a 1, but the minus beta omega term also gives you minus beta del omega del kx or minus beta kx by omega. And similarly, you have non-zero terms from del omega del ky and del omega del kz in the other two terms in the first row. But what you really need is a determinant of this matrix, and it is very easy to see that the determinant is nothing but the first top left element is nothing but the 1, 1 element of this matrix, and hence it is equal to gamma over omega times omega minus beta kx. So this is the factor by which d cube k changes under a Lorenz boost. So what is d cube k prime by omega k prime? The answer is simple. D cube k picks up this factor gamma by omega into omega minus beta kx, whereas omega prime becomes gamma times omega minus beta kx. So it's very easy to see that omega minus beta kx cancels, so does the gamma, and you are left with d cube k prime by omega k prime equals d cube k by omega k. This of course concludes our direct demonstration that d cube k by omega this of course concludes our direct demonstration that d cube k by omega is a Lorenz invariant volume. What is the advantage of having a Lorenz invariant volume? Well, let us just use this to figure out how the inner product phi comma psi suffix t transforms under a Lorenz transformation where x goes to x prime equal to lambda x. We had already seen before that under such a Lorenz transformation, psi of k, the Fourier transform, goes to psi of lambda inverse k, phi of k goes to phi of lambda inverse k. So phi comma psi, the inner product, goes over to this integral d cube k by omega k, phi of lambda inverse k conjugated times psi of lambda inverse k. Here I have deliberately written the 4 vector k in the argument of phi and psi, although earlier I had written just the 3 vector k vector for both of them. Remember that here this is a function of the 4 vector, but with k0 related to the k vector by k0 square equals k vector square plus m square. But we have already seen that d cube k by omega k is equal to d cube k prime by omega k prime, where k prime is the spatial part of the 4 vector that you get by carrying out a particular Lorenz transformation on k. Now what we choose here is the Lorenz transformation given by lambda inverse, so k prime is lambda inverse k. Now under this, all that has happened is if you replace d cube k by omega k in the measure by d cube k prime by omega k prime, which it is equal to, then you have exactly the integral d cube k prime by omega k prime phi of k prime bar psi of k prime, which is exactly the same integral as the one we started out with. And thus we see that the scalar product that we have defined here is a Lorenz invariant quantity. It does not change when you carry out a Lorenz transformation. In addition to the Lorenz invariance of d cube k by omega k, another concept that is going to be of great importance in later courses, especially if you go on to take quantum field theory, is the one we have introduced here of the scalar product between positive energy wave functions. In the general theory of the Klein Gordon field, this particular product plays a very important role, and so being familiar to this is going to help you out. Let me point out one thing. This thing is a valid inner product only if you confine yourselves to the space of all positive energy solutions. As we have already seen before, the corresponding probability density for negative energy eigenfunctions is not positive definite, in fact it is negative definite. And so if you have vectors in your space which combine both positive energy and negative energy solutions, then their inner product is not going to be a genuine inner product. While that is true, one reason why this inner product, or rather this product, is very, very important in quantum field theory is that this is a relativistically invariant construction. However, the way we have defined it involves an integration at a constant time, and that seems to belie the very fact that this is a relativistically invariant construction, simply because constant time surfaces are not relativistically covariant concepts. Different observers disagree as to what a particular constant time surface looks like simply because of relativity of simultaneity. So this particular definition does not really look very covariant. Also note that you are actually distinguishing between space and time here. The derivatives involved are del zeros, which are derivatives with respect to the time variable, and the integration is over all of x, y, z. So again, does not really look very covariant. It turns out that this can be recast in a completely covariant language, and that happens to be the following. The integral can be done here not over just a constant time surface, but any space-like surface whatsoever. That is the sigma label that we have affixed on the product definition here, as well as on the integral sign. So the integration is going to be done over some space-like surface sigma, and the integration is now of d sigma mu at x of the quantity phi bar del mu chi minus del mu phi bar chi. Of course, the sum over mu is implied, and using the double arrow notation, you can just simply write this using phi bar del mu double arrow chi. That would be a slightly compact way of writing this particular product. Let me just remind you that a space-like surface sigma is such that the interval between any 2 points x1, x2 on it is space-like, that is, the length of x1 minus x2 whole square is negative. In other words, the spatial parts are bigger in magnitude than the temporal difference. A surface at constant time, of course, has zero time difference between 2 points, so it definitely is space-like, but any space-like surface would do here. And the normal n mu to a space-like surface is a time-like vector. And d sigma mu, here the surface area element, is n mu d sigma, which is simply given by dx1, dx2, dx3 as a 0th component, dx0, dx2, dx3 as a 1th component, and so on. Once again, for the constant time surface, dx0 is 0. So n mu essentially points entirely in the time-like direction, and n mu d sigma is simply dx1, dx2, dx3 with only one non-zero component, and so d sigma mu times phi bar del double arrow mu chi is exactly the same as integral over constant time surface d cube x phi bar del 0 double arrow chi in that particular case. The question, however, is how are we so sure that this integral over an arbitrary space-like surface gives you the same result as the one that we talked about, the one where the integral was done over a constant time surface? It might seem from the definition that the value of this inner product depends on the surface that we are using to define it, and that of course would be a bit of a disaster. In order to see that this is not really a problem, let us first define a notion of the variation or variational coefficient of a function g sigma of a surface. So if g sigma is any function of a surface, and let us say we vary the surface from sigma to sigma prime so that the variation is by a small amount and a small volume omega is trapped in between the two surfaces, the variational coefficient delta g sigma delta sigma x is defined to be the change in the value of g sigma when you go from sigma to sigma prime, that is g sigma prime minus g sigma, divided by the volume trapped between the two surfaces, omega x, and you take the limit as omega goes to 0 in order to get the variation exactly at the point x. What you are doing is varying the surface slightly around the point x and trying to find how much the function of the surface changes over the volume trapped between, and then as this volume shrinks down to a 0 volume so that the two surfaces come and coincide with each other, the ratio in the limit becomes your variational coefficient here. Now, one case where this variational coefficient becomes very important is where g sigma is a flux of a 4 vector f mu through the surface sigma, that is the integral d sigma mu f mu over the surface sigma. Then the variational coefficient, proceeding from the definition, simply becomes the difference between the two fluxes through sigma prime and sigma, and that's nothing but a total flux which exits the surface, which is formed by the union of sigma prime and sigma. Remember, our omega, the thing which is sitting in the denominator, is actually the volume trapped between the surface sigma prime union sigma, and a simple application of the Gauss theorem in 4 dimensions simply converts this integral over the surface to a 4-dimensional volume integral d4x of del mu f mu. This is exactly a generalization of our 3-dimensional Gauss theorem with just one additional variable thrown in. Note that in the limit when omega goes to 0, the 4-dimensional volume integral is effectively being done over a very, very tiny volume around the point x. So there del mu f mu can come out of the integral since it hardly gets a chance to vary, and then the integral simply becomes del mu f mu at x times the size of the integral d4x over omega, which is exactly the same as the denominator omega x. Cancelling it out and taking the limit gives us the result that this variational coefficient of g sigma is nothing but the 4 divergence of f mu del mu f mu. So the rate at which a flux varies when you change the surface slightly is nothing but the 4 divergence of the corresponding 4 vector. Let us now use this result to find out how much our inner product phi chi evaluated on the surface sigma varies when we change the surface sigma slightly. So we are calculating our variational derivative here. Note that the inner product here is actually a flux of the vector phi bar del mu double arrow chi, that is phi bar del mu chi minus del mu phi bar chi. Of course there's an extra I in front, but that's just an overall factor. According to the result that we had worked out just now, this is actually the 4 divergence del upper mu of I times phi bar del mu chi minus del mu phi bar chi. Now when you calculate the 4 divergence, the I simply moves out as an overall factor, but then if you are calculating del upper mu of phi bar del lower mu chi, this gives rise to 2 terms, del mu phi bar where you are taking the 4 divergence of the first piece times del mu chi plus phi bar times del upper mu del lower mu acting on chi. And you get similar 2 terms from the second piece minus del mu phi bar chi's 4 divergence. But notice that the terms del mu phi bar del mu chi is common in both, and so they cancel, and you are left with phi bar box chi minus box phi bar chi. Now, if my wave functions phi and chi obey the Klein Gordon equation, then box chi is actually minus mu square chi, and box phi bar is minus mu square phi bar. So if you just substitute those values in there, it turns out that this variational coefficient cancels. So what does this tell you? It tells you that if you were to vary a surface over which the integral is being done, the inner product phi comma chi sigma does not vary. So ultimately, the scalar product of 2 wave functions obeying the Klein Gordon equation does not depend on which space-like surface is used. And this, of course, also tells us that in the special case where the 2 surfaces used are one at some constant time t0 and another at some other constant time t, there is no change in the inner product. This is, of course, something we had already established before when we showed that phi chi at t is actually independent of the parameter t. Let me remind you once again that while we are calling this an inner product, it really is a valid inner product if your Hilbert space consists of positive energy states only. If you take all possible solutions of the Klein Gordon equation, then this is not a valid inner product simply because it's not positive definite. Despite that, this is actually a pretty useful tool to have even when you're talking about all solutions of the Klein Gordon equation. One of the major reasons behind that being that wave functions corresponding to definite energy values, be they positive or negative, are all orthogonal according to this particular inner product. And so this is very useful in separating out contributions due to different positive frequency or negative frequency components, or positive energy or negative energy components. Now, as we have seen, the reason why this does not work as an inner product for all possible solutions is that, especially for negative energy states, this quantity ends up being a negative number. In fact, the integrand becomes negative. This, of course, prevents us from interpreting this quantity, the rho that we had talked about for the Klein Gordon equation, as a valid probability density. However, if you think about it a bit, if you were to multiply this by a charge, then you can interpret this perfectly nicely as a charge density. So in a way, the negative energy states are states which correspond to negatively charged particles, which are otherwise identical to the original one. We can extend this idea to arrive at the concept of antiparticles. Now, although we started out with a single particle theory, it seems natural to talk about antiparticles and hence particle-antiparticle creation within this framework, and that is not so difficult to understand. After all, if you were to confine a particle to a very small volume, the overall energy available becomes too big because of the uncertainty principle, and that might lead to creation of a particle-antiparticle pair. This, of course, is something which is allowed only in relativistic physics. And this is the reason why relativistic quantum mechanics inherently is more difficult than non-relativistic quantum mechanics, despite having a larger amount of symmetry. It's just that you cannot really treat relativistic quantum mechanics as a single particle theory. Particle creation annihilation becomes imperative whenever you try to confine a particle to a very, very narrow region. We are going to continue with our current discussion of the Klein Gordon equation as a single particle equation in the next lecture, which will hopefully be the last on the Klein Gordon equation before we move on to the Dirac equation. We will try to see how far you can push this picture, and we will also see some problems which occur when you try to push it too much. Once again, let me stress that the real reason for the difficulty is that any relativistic quantum mechanical theory which will end up with pair creation at high enough energies, which means small enough confinement regions, and this will automatically cause problems for a single particle theory. In this course, we are only going to talk about single particle quantum mechanics, but these ideas are going to come in very handy when you go on to learn about quantum field theory. Many of the techniques that I am discussing here will be used there almost without any change. So until the next lecture then, goodbye.